Up until now, we've learned inferential procedures, that is, tests and confidence intervals, for what we'd call the one-sample case. That is, we've been interested in a single proportion, such as the percentage of people who support the mayor, or a single mean, such as the mean body temperature for healthy adults. However, many questions that we might want to study require us to have two sets of data, or to look at the same measurement taken under two different conditions. So now we're going to look at expanding our statistical toolbox to include tests and confidence intervals to see if two measurements or two groups differ. We're going to go back now to our anthropology data and measurements on 400 skeletons, in particular estimates at age of death and how those estimates differ from actual age at death. We've looked at the estimates given by the Dagrange method, in which age estimates were made by examining the first rib. Previously, we learned that the Dagrange method tends to underestimate the age of death, with the errors in age estimation negative for more than 75% of the observations. As we can see by the third quartile, which is negative, and we can see that our average or mean error of age estimation is negative 14 years. So on average, the Dagrange method underestimates the age of death by more than 14 years. When we first introduced this data set, we also discussed the Saatchi-Brooks method. This method estimates the age from the pubic bone, a weight-bearing part of the body, so it may perform differently than the Dagrange method. Looking at some summary statistics in the box plot for the error in age estimation from the Saatchi-Brooks method, we can also see that it tends to underestimate. With a third quartile of 0, so 75% of our observations are 0 or less, and an average estimated error in age estimation of more than 7 years. So both methods underestimate the actual age. But maybe the Saatchi-Brooks method performs a little better. If we look at the box plots for the two methods side by side, we can see that the values for the Saatchi-Brooks method seem a little closer to 0, which is what we'd get if the actual and estimated age were the same. But there's a lot of overlap in these box plots. So you may wonder, is the difference between the two methods significant? Before answering that question, there is something fundamentally wrong with the representation in these box plots. The estimates by each method were taken on the same skeletons. But we don't know this from the plot, in which we can't tell how the measurements on each skeleton coincide. For example, our largest underestimate using the Dagrange method was a whopping 60 years below the actual age. Using the Saatchi-Brooks method, the largest underestimate was only 36 years. But are these even the same skeleton? Because these side-by-side box plots don't match up measurements on the same skeleton, this isn't the best representation of our data. This is an example of matched pairs. Matched pairs is useful when we want to compare two conditions or treatments or methods, and we are able to compare them on the same observational or experimental unit, or on two very similar matched units. This could be the same subject or skeleton, or perhaps something like twins or siblings. Some examples of matched pairs include, of course, comparing two methods on the same skeleton. Another common example is pre- and post-test scores. For example, I could test you on your statistical knowledge before the course, and then at the end to test the effectiveness of the course. Sometimes we can design a study to compare matched measurements taken at the same time or place. For example, if we wanted to compare sales in two branches of a store, we could measure sales in each branch on the same weeks. So then the sales are matched by week. Or in an experiment with two treatments, we could first give each experimental unit one treatment and then the other treatment for comparison. Such an experiment is called a crossover study. In a crossover study, we don't randomize treatments to experimental units, since each unit gets each treatment, but we do randomly determine the order each unit gets the treatments, in case the effect of one treatment might be affected by the treatment that precedes it. Matched pairs is a form of control. We are controlling for all the variables that naturally vary among independent subjects or experimental units or observational units by making our comparisons within these subjects or units. As a result, there is less variability or greater precision, and thus more power in our tests and narrower confidence intervals, in our estimate of the difference between the treatments or conditions being compared. Up to now, our inferential methods have assumed that all our observations are independent. Match pairs aren't. If they were, we wouldn't get the greater precision that we're looking for in our comparisons. So we have to take that into account in our analyses. So, how are we going to carry out the analysis to compare the Degonghi and Saatchi-Brooks methods? The general approach is to treat each pair as one observation, and then they'd all be independent, since each skeleton is independent. For each skeleton, we calculate the difference in the error in age estimation between the Saatchi-Brooks and the Degonghi methods, and then we carry out the analysis on these differences. That's one measurement per skeleton, and we already know methods for one measurement. And in particular, comparing the means of these two methods will become looking at the mean of the differences. Before we proceed, there's one small item I need to point out about these data. For two of the observations, the Saatchi-Brooks estimate is missing. Different statistical packages use different symbols for missing data. In R, the symbol is NA. I originally chose the sample of 400 skeletons that we've been working with in order to have a Degonghi estimate for each, so the skeletons all had their first rib intact. But that doesn't mean that all other bones were intact, and indeed 2 of our 400 skeletons had damaged or missing pubic bones, so a Saatchi-Brooks estimate wasn't possible. But we don't expect that a missing bone is related to age at death or its estimate, or sex or BMI if we analyze that. So we don't expect that leaving out missing observations will bias the results. So we'll continue with the 398 skeletons, for which we have both estimates for both methods so that we can compare them. Let's take a quick look at these 398 differences. From the plots, we can see that their distribution is fairly symmetric, and it's centered above 0. Indeed, the average difference is 6.854. So the difference in the error in the two methods is, on average, almost 7 years. Since both methods tend to underestimate age at death, so their errors are negative, and in this case we're subtracting the Degonghi errors from the Saatchi-Brooks errors, a positive mean is an indication of higher error estimates in the Saatchi-Brooks method, which means that they're closer to 0 on average. So it seems we have an indication that the Saatchi-Brooks method is more accurate. One more statistic to note from these differences, the standard deviation of them is about 11 years. Let's call the difference between the error in age estimation between the Saatchi-Brooks and Degonghi methods D. To test whether the mean error in age estimation differs between these two methods, we'll specify our null hypothesis that there is no difference, or that mu d, the mean of the differences, is 0. And we'll test that against the two-sided alternative of some difference between the mean of the methods, so the mean of the difference is not 0. The statistics we'll need from our data are the average of the differences, which is 6.854, and the standard deviation calculated from the 398 differences, which is just over 11. As we've already seen for a one-sample test of the mean, our test statistic is the sample average, standardized by centering around our null hypothesis value, in this case 0, and dividing by the standard deviation of the mean, which is the standard deviation divided by the square root of n, and this gives us approximately 12.37 for our test statistic. If the null hypothesis is true, this test statistic should be a value from a t-distribution with 397 degrees of freedom. With such a high degree of freedom, this will be quite close to a standard normal distribution. And in a standard normal distribution, we know that 99.7% of the data values are within 3 standard deviations of the mean, or within -3 and +3. So a value greater than 12.37, or more extreme in the other direction, less than -12.37, is very unlikely. And indeed, the p-value in this case has 29 zeros after the decimal place before it gets to a significant digit. So it's very, very small. With such an extremely small p-value, we can conclude that we have extremely strong evidence that the null hypothesis is not true, That is, the mean of the difference between the methods in the errors in age estimation is not 0. So the Saatchi-Brooks method and the Dagrange method don't give the same mean error in age estimation. We noted earlier that the average difference between the methods was positive. And this is an indication that the errors in age estimation were closer to 0 for the Saatchi-Brooks method. So the Saatchi-Brooks method is giving age estimates that are closer to the actual age. Remember that the Saatchi-Brooks method uses the pubic bone, a weight-bearing bone, where the Dagrange method uses a rib, a non-weight-bearing bone. So an interesting follow-up question might be to further investigate whether weight-bearing bones give more accurate estimates. Of course, this is an observational study, not an experiment, so we need to be careful not to overstate our conclusions. We can't say anything that implies cause and effect. But we can say that for the set of skeletons that are being examined here, there is strong evidence that the mean error in age estimation is not the same between the two methods. As an estimate of the difference in the error in age estimation between the Saatchi-Brooks and the Dagrange methods, we have the sample mean of the differences, which was almost 7 years. Even better would be to include a range of plausible values for what this mean difference could be. And for this, we know how to construct a confidence interval. Suppose we want to be 95% confident that we capture the true mean difference in our interval. Since we have differences for 398 skeletons, we'll need the values from a t-distribution with 397 degrees of freedom, so that the area between them is 0.95 or 95%. These critical values that we need are negative and positive 1.966. And our 95% confidence interval for the mean of the difference is then our sample mean, 6.854, plus or minus this critical value from the t-distribution, 1.966, times the standard deviation of the mean, which is the standard deviation divided by the square root of the sample size. That gives us a 95% confidence interval from about 5.76 to 7.94. So we estimate that the true mean difference in the error in age estimation between the Saatchi-Brooks and Dagrange methods is possibly as low as 5.76 or a little under 6 years, and as high as almost 8 years. From our statistical test, we had very strong evidence that the mean of the differences was not 0. And correspondingly, we don't see 0 within this confidence interval. For all of the inferential procedures that we've learned, we need independent data. That is, we need all of the observations to be independent of each other. In matched pairs designs, this isn't the case. Certainly, if we have two measurements on, say, the same skeleton, we expect that those two measurements will be related to each other. However, we can combine them into a single measurement, typically by taking a difference, as we did in this video. And then we have one set of independent observations, as long as the skeletons are independent, which we can analyze using the one-sample procedures that we've already learned.